Voy a presentar a nuestro conferencista en inglés, o esa cosa que es mi inglés, debido a que tenemos en la audiencia participantes que no hablan castellano. Bueno, all of you know that our first speaker is Pedro Massey from the Instituto Argentino de Matemática and the Universidad Nacional de La Plata. Well, Pedro is dearest, three times dearest member of the Institute. He is gentle, kind, amicable, attentive, a true gentleman in the body of a mathematician, or better, the other way around, a true mathematician in the body of a gentleman. Pedro got his PhD degree from La Plata. His advisor was Dimitri Stojanov. Since then, they have been collaborating, a sort of yin and yang collaboration, because if you know Demetrio, as quiet Pedro, as loud Demetrio. And well, in any case, a very fruitful collaboration, not only in terms of quantity, but also in terms of quality. Of course, Pedro has many other collaborations, for instance, with Martin Archerami, who was his postdoc supervisor in Canada. When younger, he got the Julio Rey Pastor Prize, a prize that the Argentinian Academy of Science gives to promising young mathematicians. I don't know Pedro very well. Many of you know him better than me, but I know for sure that his talk is going to be very interesting. Muy interesante, but not Misha Kotler's muy interesante, okay? So, welcome. He's going to talk about action of a restricted unitary group.
Yes. Thank you very much, Stefania, for the introduction. And thank you for this speech today. I'm deeply honored to be a member of YAM. I've been coming here to YAM for about 20 years now, but the first 5 years, I came here with no formal affiliation. And I was really treated like if I was a member of YAM. And I received a lot of support, both psychological support and financial support, because when you're young and you're trying to start mathematics, that could be hard. Here in YAM, I found a place where, well, you learn a lot, you share a lot of mathematics with people, so thank you very much. Then, okay. So there are many things that I would like to say, but I just say thank you very much to the institution. So the talk I would like to share with you today is about these actions of restricted unitary groups, which is joint work with Eduardo Pimiento, who also works here at YAM. So we will need a little bit of language and notions to state the problems and maybe some solutions. So we will consider a multi-dimensional state-order context Hilbert space, and we will be dealing with these operator ideas that are just bilateral ideas of the algebraic boundary operators at the image. For example, we have finite band operators, ideas, compact operators, format ideas. If you take t greater than 0, less than infinity, then we can consider Chapman T ideas. because these compact operators such that this space is finite, this space can be computed as this matrix here, the series of singular values of t to the power t, where these singular values will appear later on, and they are always considered arranged in this decreasing way. For example, if t is greater than 1, there's infinity, then Chapman ideals are symmetrically normed here, with the norm given by the t norm here that satisfies certain properties. For example, it is stronger than the greater norm, it has this some explicativity property. Notice that we have like this narrowly algebraic idea and this normed idea. So we have to take into consideration this fact. And so if you take, say, a non-zero improper operator idea of zero state, then these inclusions are well known. Okay, we can finite operators, this including compact operators. And given two compact operators, R and T, we see that R is parameterized by T, in this way, if you sum the first n singular values of R is less than or equal to the first n singular values of T, these are the largest singular values of R, which is the largest of T, for every n greater than 1. And we say that an operator idea is arithmetically closed if it has this kind of hereditary property. Whenever you have a compact operator R, such that R is parameterized in this sense by some T in the idea, then R also like possible. For example, finite branch operators, Chapman ideas for T between T and 1 are not arithmetically enclosed, while Chapman ideas for T between 1 and infinity are arithmetically enclosed. And the reason why we consider these arithmetically enclosed ideas is because these ideas have some sort of analytical structure, supposed to marry algebraic ideas. But the analytical structure they have is quite soft. Okay, so when we will consider proper operator ideas, BFH, once we fix this proper operator idea, we can consider this restricted invertible group, which is the set of all invertible operators such H that can be written in this way. If invertible can be written as the identity plus an element in the idea. And the restricted unitary group induced by this idea J is the set of all unitary operators that can also be written in this way. Identity plus an element in the idea. So the restricted invertible group is a subgroup of the group of invertible operators. And the restricted unitary group is a subgroup of the group of unitary operators. Since we are considering proper ideas, so that they are containing compact operators, these inclusions are proper. And whenever we have a boundary operator at the moment, we will consider this restricted unitary orbit to operator A, which is a set of all these unitary conjugates by unitaries that are actually restricted unitary. Okay. Notice that this is a proper subset of the usual three unitary orbit of the operator. Okay, so we are considering like these unitary conjugates of A given by these unitaries, which in some sense they are close to identity in the sense that they can be written this way. So we expect these unitary conjugates to be rather close to A. We will discuss later. We will need another ingredient for this, which is a fixed orthogonal basis of the zero space and the corresponding diagonal diagram with fixed orthogonal basis, which is a set of operators that are diagonal to this basis. And this diagonal algebra has this so-called algebra, which is the maximal dimension of zero space. And elements in the diagonal algebra are always normal diagonal operators. Okay. In the fact, we can now state the problem that we were interested with the water. which is this form of uj generalization with respect to basis E. So we fix this operator of Vij, we fix this operator basis E, we consider the Young algebra before. The problem is both sides. The theta mathematics derived is the following. Given a boundary operator at the H, characterized when the intersection of this restricted unitary orbit of A with the diagonal algebra is unique. So we somehow want to rotate this operator A in a rather controlled way because we would like to consider this unitary conjugate of A by this special unitary, restricted unitary. And we would like this unitary conjugate to lie now in this diagonal. In this case, we say that A is usually diagonalizable with respect to this fixed orthogonal. This is strongly depends on the idea and on the orthogonal base. So we are considering this restricted unit. There's a very, very simple observation here, which is the following. If this intersection is non-empty, you can take a B here section from on the one hand, B is the unitary conjugate of A, some restricted unitary U, and B is in the diagonal algebra. So B is normal and diagonalizable, and then so should be A. A should be also normal and diagonal. Moreover, since we are considering this special unitaries, it is not difficult to show that the unitary conjugate B differs from A in an element of the U. So this unitary conjugate B of A is close to A in the sense that this difference has in the U. Okay, so here we have our problem. We have some necessary conditions for this intersection to be here, which are A normal and diagonal. And maybe the simplest case of a normal diagonal operator is a following. So we first consider this case. I mean, this case was already solved when we tried this problem. And the solution was obtained by Pedro in the following context. So if you are given two orthogonal projections such that the difference of this P and Q of this pair is a compact operator, then we can always consider the index of the pair, which is denoted in this way, which is simply the difference of these two dimensions. And this difference will always be an integer number. So the index is the dimension of the intersection of the null space of Q, the range of Q, minus the dimension of the intersection of the range of Q and the null space of P. And this index is actually a Fresnel index. When you consider this transformation, P and Q restricted to the range of Q, acting from the range of Q to the range of P, then the index of the pair is nothing but the Fresnel index. Pascal and Leroux showed that given two projections, then the difference of the projection lies in this operator Dij, and the index of the pair is 0 if and only if there exists a restricted unitary operator that conjugates P into P. And with this result, then Leroux was able to show this operator proposition that given a orthogonal projection P, then P is uj diagonalizable with respect to the operator P, if and only if there exists a projection in the diagonal algebra such that the difference between P and E lies in the idea. So we are missing here a condition in some sense, which is that the index between P and E to be 0 for this to work, I mean, for this theorem to be applied here. But you can somehow arrange things for that to happen. If you begin with a diagonal projection, such as this difference is an idea, then you can replace this original projection by some finite-dimensional configuration of P, which we call Euclidean, that's also in the diagonal algebra, that's also such that this difference is linear, but now this index equals 0. And so by Pascal's result, we got that there is the strictly unitary operator of conjugate P into each integral, which is an element in the diagonal algebra, so P is uj diagonal. We will use this remark, this proposition, to show, to characterize when normal operators with finite spectrum are uj diagonal. So in this case, we will consider normal operators with finite spectrum, which are automatically diagonalizable. And in this case, we consider finite sequence of projections, nuclear orthogonal projections, that sum up to identity and pairwise different complex numbers. And so we can represent this operator A, this linear combination. Here, the PIs will be the spectral projections of this normal finite normal operator A with spectrum, and this lambda I will be the spectrum. In this context, A is UJ diagonalizable, meaning that this strictly unitary conjugates A into an element in the diagonal algebra. If only if this unitary conjugates each spectral projection of A into some projection in the diagonal. That's quite easy to do. With this remark and some quite elaborate arguments, you're all to the following characterization. Given this normal operator with finite spectrum, then A is UJ diagonalizable. If only if there exists a finite sequence of projections in the diagonal algebra such that each spectral projection of A differs from this diagonal projection by element of the view. Interestingly enough, Loro was not actually interested in solving this problem, but was interested in studying what's called Anderson's index of fluxing for a sequence to be the main diagonal of the normal operator with finite spectrum, which is a different problem. But along the way, he showed this result, and moreover, he considered certain techniques which were really useful for us. So the first step would be for us was to find a different characterization of this very same problem. I mean, we will consider again normal operator with finite spectrum, and together with Eduardo we show a different characterization of when this operator A is UJ diagonalizable. We show that A is UJ diagonalizable if only if there exists projections in the diagonal algebra. And notice that we are not asking these projections to be nuclear orthogonal, neither to sum the identity, to add up to the identity. But we even such that these two sums are in the idea. This sum of identity PI to PI should be in the idea of this condition. These two conditions are independent, so we need both conditions. It is not difficult to see that if we can check Loro's conditions, then we can check our conditions here. But it's not that easy to say that if we have our conditions here, then we can check Loro's conditions, because as opposed to Loro's criteria that take these different separately, indices are separately, we are considering this superposition of operators. Okay, so we are asking this sum to lie in the idea. And these projections here are not nuclear orthogonal, so it's not easy to from this summation to get that each term, for example, lies in the idea. But okay, so here we have our recommendation. But the nice thing about this new characterization of UJ diagonalizable operators is that it extends in a rather trivial way or natural way to consider normal diagonalizable operators with infinite spectrum, which was one of our main results. So in this context, given a normal diagonalizable operator, we will consider its point spectrum lambda I, now for I between 1 and infinity, and we will consider the spectral projections of this normal operator, normal diagonalizable operator, PI. This is a sequence of nuclear orthogonal projections summing up to identity in strong operator topology, and allow us to represent A in this way. And again, this operator is UJ diagonalizable if only if we can find a restricted unitary that conjugates its spectral projections of A into some diagonal projection. And our criteria is as follows. Let A be a normal diagonalizable operator with infinite spectrum. If we assume that there exists a sequence of projections in the diagonal algebra such that now these series here both are in the idea, where the convergence is considered a weak operator topology, then A is UJ diagonalized. Notice that these two series are essentially the same as these sums, but instead of writing n, we wrote infinity, and this corresponds to sufficient conditions for UJ diagonalization. That is, whenever you can find this sequence of diagonal projections, such as both these series lie in the ideal, then A is UJ diagonalized. It would be nice to have a converse, and you have a converse, but then, in that case, you would need to ask the idea to cooperate. Conversely, if A is UJ diagonalizable and the ideal J is an arithmetic close ideal, then there exists a sequence of projections in the diagonal algebra such that the equation 1 holds. Okay. So, for example, if the idea is arithmetic mean close, then the existence of this sequence of projections such that the conditions in equation 1 holds is sufficient and also necessary for UJ derivatives. So we have a characterization. Let me consider some remarks related with this statement. For slide. On the other hand, if J is not arithmetic mean close, then the second statement, I mean the converse here, might not hold. It's not going to change. And we have an example considering this finite rank operators, which is an ideal, in the sense that algebraic ideal, but it's not an arithmetic mean close ideal, and the result is not good. If the series that we have considered in the statement converge, then we can check Lorentz condition. This difference between Pi and this diagonal projection, I mean, the difference between the spectral projection of A and this diagonal projection is an ideal for every I. But this last condition is not sufficient for UJ diagonalization. It means that Lorentz criteria does not extend, at least not in a trivial way, to characterize UJ diagonalization in this infinite spectrum case. And when the series converge in the world operator topology, in the weak operator topology, then they also converge with respect to the topology given by the norm, which is strong convergence. And if the idea is arithmetic mean close, then we have a characterization. If this operator is UJ diagonalizable if and only if there exists a sequence of diagonal projections such that these both conditions hold. Let me see. I would like to maybe go through some aspects of the proof of this. Okay. So, assume now that this normal diagonalizable operator is such that there exists a sequence of projections in the diagonal algebra for which both these series lie in the operator ideal. And remember that these diagonal projections are not mutually orthogonal. We haven't asked them to be mutually orthogonal. But it turns out that the previous conditions imply that there exists an index I0 such that the tail of the sequence of these diagonal projections are mutually orthogonal. And in that case, we can consider the projection E, which is the sum of this tail of projections, that since they are mutually orthogonal, they sum up to some projection E. P, which is the sum of these spectral projections that were always mutually orthogonal, so this also projection, and S, this operator written this way, that is a boundary operator, in this series converging the strong operator topology. And notice that S, in this case, when restricted to the range of P into the range of E, turns out to be an invertible operator, such that P minus S, as operators of B of H, lie in the idea. And the nice thing about S is that it intertwines the projections EI and PI. Okay. And now we can consider the partial isometry, which is the polar factor in the polar decomposition of this operator S. And since S intertwines EI with PI, then this partial isometry conjugates PI into EI for every I greater than I0. So in a sense, we are having some control of the tails of these two sequences of projections. And moreover, we can show that the initial space of P equals the range of P, and the final space of P coincides with the range of E, and B minus P and E minus P lie in the idea. You can check this by using the explicit expressions for S, for P. And now, since the difference between E and P is in the idea is a proper idea, the difference is a compact operator. And therefore, we can try to compute the index of this pair of projections E and P. And it turns out that this index equals 0, which is a non-trivial fact. And this also implies, in a non-trivial way, that there exists U0 restricted unitary operator that now conjugates the tail of the sequence PI, these spectral projections, into this nuclear orthogonal projection CI for I greater than or equal to 0. Okay. And moreover, following Loroz's type of construction and arguments, we can somehow fix what's happening with the initial projections. Notice that we have somehow solved the problem for. So I mean, we are finding a restricted unitary that's conjugating spectral projections into diagonal projections, but from I0 until the end. But what about the first initial projections? So we can construct these auxiliary diagonal projections EI tilde for the I between 1 and I0, and a restricted unitary operator that now conjugates the initial projection Pi into this Pi tilde for I between 1 and I0, and the final projection Pi into EI for the I greater than or equal to I0. So this restricted unitary operator conjugates all spectral projections of A into diagonal projections, in the sense that these are projections into the diagonal algebra, and that implies that this unitary conjugates of A lies in the diagonal. And the key fact that allows us to compute this index follows from extensions of previous results by Eduardo, dealing with the geometry of partial isomorphism. Okay, so that would be the proof, I mean, a sketch of proof of the first part of the result. So that the existence of this sequence of projections verifying these two properties implies that A is UJ than X. There are many technical facts hidden behind this key fact, this claim. I will not bother you with those besides. And what about the converse? For the converse, we assume that the idea is arithmetically enclosed, and we also assume that A is UJ diagonalizable, so there exists a restricted unitary that conjugates A into a diagonal operator. And in this case, we simply define this projection CI to be the unitary conjugates of PI. It should be in the diagonal algebra because there are spectral projections of A, and this unitary conjugate lies in this diagonal algebra. And now these projections CI are multi-orthogonal by construction. Moreover, they are identical. And in this case, we would like to show that this series lies in the idea, is in the idea. So, but rather straightforward computations show that this series can be written in this way, this last identity. This series can be written as the difference of these two terms. The first term is U star minus identity times U. Now, remember that U is a restricted unitary operator. That means that the difference between U star and identity is an element of the idea. So we have here a factor in the idea times U. This term is in the idea. And what about the second term? The second term has two factors, U and this first factor here. But this first factor has a rather nice structure. This construction is quite well known. It's called the so-called pinching. So since EI are nuclear orthogonal, this corresponds to a block diagonal compression of the operator U star minus identity to the block diagonal algebra. And it is well known that the pinching of U star minus identity is summarized by U star minus identity, in the sense I've mentioned at the start of the talk. And if the idea is arithmetically enclosed, we have this sort of hereditary property. If this operator is in the idea, which is in the idea because this difference and U star is a restricted unitary operator, if this is an idea, and this is summarized by an element of idea, then this is also an idea. So we have that this factor is an idea, now the second term is an idea, and this series is the idea. And this shows how is that the condition that the idea is arithmetically enclosed plays a role here. And I write down some consequences. I should be clear and say that these are not actually consequences of the main result that I just mentioned. but there are consequences of the techniques that we needed to prove that result. In particular, there are consequences of this key fact that I haven't really explained yet, but it is in the same vein ideas. So Beltita also asked about, well, Beltita, Patnaik, and Weiss included this notion in their work. Consider two orthogonal bases of the Hilbert space H, F given by the sequence Fn and G given by the sequence Gn, and they said they define this to be J unitary equivalent if we can find a restricted unitary W that maps each Fn into Gn. Okay, so we can rotate this orthogonal basis A with the orthogonal basis G by this restricted unitary W. So W is a perturbation of the identity. W doesn't move things too much in some sense. And well, okay, so we have this notion, and the implicit question here is whether we can characterize when two orthogonal bases are J unitary equivalent. And we had this characterization. We now fix a third orthogonal basis of the Hilbert space. Now this is fixed, and having F and G, we define these two unitary operators, U1 and U2, that are given in this way. U1 maps each of the elements of this fixed orthogonal basis En into Fn, and U2 maps the Ens into the Gns. And our result state it's as follows. Given these two orthogonal bases of the Hilbert space, then they are J unitary equivalent if and only if the difference between these unitary operators is in their view. Okay, there's something not nice about this is that we don't really have a characterization of J unitary equivalent basis or orthogonal basis in terms of vectors, but in some cases you can get you can write down this condition in a somehow explicit way using the vectors in the orthogonal basis. For example, if you take the idea to be the Hilbert-Schmidt ideas, then the fact that F and G are J unitary equivalent is well, it's the same as asking this difference to be the Hilbert-Schmidt operator now, and you can write down that this difference is in the Hilbert-Schmidt operator if only if we get this condition that the series of the square of the norms of the differences is bounded, and this was well known. But just to get a feeling of what this means. Now, in the case of the compact operators, the idea of compact operators, the authors mentioned, well, we don't really know. We haven't found any characterization, but we get our characterization, which is now F and G are J unitary equivalent if only this difference is a compact operator, and we can write down some sort of condition translating these differences to compact operators in terms of an epsilon element. So for epsilon greater than 0, so to system index and 0, like that for every n greater than 0, we have this condition that involves the elements in the orthogonal basis. Okay. And so, but the thing about orthogonal basis is that you can consider them as particular cases of frames. And we were interested about frames also. So what about extending this notion of J unitary equivalent relations between orthogonal basis to the cases of frames? We wanted to do that, and so I would need to write down some definitions for this to have sense. So given a closed subspace of the Hilbert space H, and fixing orthogonal basis of Hilbert space, recall that the sequence is not in S, is a frame for the subspace S. This is maybe you have heard about frames for complete Hilbert spaces. We are considering here frames for closed subspaces, which is somehow a little bit localized. But this is a frame for subspace S, if only if there exist these two constants, such as a so-called frame inequality holds for every vector in the subspace. And in this case, we can define the so-called synthesis operator of this frame F, which is given this way. For this fixed orthogonal basis of the Hilbert space, we let Tf act on En as Fx, the member of this frame. And Tf turns out to be a bounded closed range operator whose range is the subspace S. And we can also define the so-called frame operator, the frame of subspace S, which is given by TF here, which is an invertible operator when acting on its range, which is the subspace F again. And well, frames are called parseval in this context for subspace F if its frame operator, if their frame operator contacts with a orthogonal projection into the subspace F. And whenever you have a frame, you can compute the so-called canonical dual of that frame. In this case, it can be written as the sequence of Newton-Ross the frame operator of the vectors Fn, which is also a frame for subspace F, and satisfies the so-called canonical representation formulas for vectors in the subspace. Okay, and whenever you have a frame, then you can compute the so-called associated parseval frame of this frame F, which is called this F tilde, which is given by the Hilbert single inverse of the square root now of the frame operator, except which by construction is a positive operator acting on each F. So these are some elementary notions of frame theory, but we need them in order to state our results. And so we suggested that we could consider this equivalence between now frames. So we have F and G, be two frames for closed subspaces S and T, not necessarily the same subspace, or S and T could be different. And we consider an operator idea, proper operator idea of V of H. Now we say that these two frames are J equivalent if there exists a restricted invertible operator, G, can be written this way, so that G minus identity is element of idea that maps each Fn into Gn. And we say that F and G are J unitary equivalent if, well, there exists a restricted unitary operator that maps each Fn into Gn. So this second notion extends this notion by the beta at night maps to the context of frames. Okay, so it would be nice to have some, if we could, to have some characterizations of J equivalence and J unitary equivalence. It turns out that there is a notion of equivalence between frames developed by Baran many years ago. This can be considered, these notions above can be considered as localizations of Baran's notions of equivalence. Well, localization means that we are taking into consideration an idea. Okay? And they apply for frames for subspaces and arbitrary operator. There is one more notion, sorry. Two frames for closed subspaces are so-called weakly similar if there exists a bounded invertible linear transformation from S to G that maps each Fn into Gn. And now we can state our results related with this equivalence. So given two frames Fn and Gn for closed subspaces S and T of H, the following statements are equivalent, that F and G are J equivalent in the sense that there exists an invertible operator mapping each Fn into Gn. That's equivalent to the fact that the difference of the synthesis operators of F and G is an element in the idea, and that these two synthesis operators have the same null space. This can also be written or interpreted in the frame language, but from an operator point of view, we just write it this way. Now, that's equivalent to the fact that F and G are weakly similar, and the difference of the synthesis operators are in the idea, is in the idea. That's also equivalent to the fact that canonical duos, F sharp and G sharp, are also J equivalent. And if any of these conditions hold, then the difference between the orthogonal projections onto these two subspaces S and T is an idea, and the index of these pair of projections equals 0. That means that S and T should be a closed subspaces in some sense and compatible. Moreover, if the ideas are inherently enclosed, then these previous conditions are also equivalent to the following one. The associated parseval frames F tilde and G tilde are J unitary equivalent, and the difference between the frame operators of F and G is in the some sort of technical condition. And there's something interesting here, that if F and G are frames that are J equivalent, notice that the difference between the synthesis operators of these two frames is in the idea. So intention here, for example, is symmetrically normal here. For example, shading here for P greater than 1. Then we can measure the distance between F and G in terms of the norm of the difference. And that can be done in a straightforward manner. We came up with the approximation problem in this context as follows. And given two frames for graph spaces S and T, and consider for the purposes of the result this J to be this shocking P idea for P strictly greater than 1, less than infinity, because we want norm here to be a strictly convex norm. And assume that F and G are shocking P equivalent. Then, as we said before, the difference between the synthesis operators is in the idea, and we can measure the distance between these two frames as the P norm of the difference of the synthesis operators of these frames. And we have this result for this idea, shocking P idea, P is strictly greater than 1, less than infinity, and given a frame for close-up space S, let us assume that F is shocking P equivalent to some G1, where G1 is a partial frame for a close-up space, say T of H. And so we are assuming that F is shocking P equivalent to G1, where G1 is some partial frame for some close-up space H. Then it turns out that F should be shocking P equivalent to its own associated partial frame, and we have this inequality. So its own possible associated partial frame is the closest partial frame to respect to this method. And since we are considering this case, the norm is strictly convex, and so the case of equality is characterized by this principle. If we have equality here, the distance between F and F0 equals the distance between F and this G1 here, then G1 should be the associated partial frame. And this result extends the so-called symmetrical approximation problem for frames achieved by time, force, divided. Okay, it is that would be for
Comments, questions? Could you give the
sorry, I must speak in Spanish. Me quedé con toda la equivalencia de frames. Vos necesitas un inversible que mande uno del otro, entonces tiene que tener el mismo núcleo. Cuando no tiene el mismo núcleo, ¿hay alguna manera de relacionarlas para que estén pegadas vía integral?
So, let you ask what happens if you have this condition, but you don't have this condition? So,
eso es porque siempre que hay un inversible que manda uno en el otro. O sea, tu definición involucra que hay un inversible que manda uno en cada F, claro. Y eso es una relación que en general obliga a esa condición.
Okay, yes. If these are the equivalent, then this is forced to be true, because we are having this invertible operator acting, say, this synthesis. This action to the left doesn't modify the null space. But okay, so if you have the difference here in the real, then you can compute, say, the index of the curve projections that correspond to the null spaces, the frames, and that would give you an integer, and we can somehow decompose also this. Although G, say you fix F, you consider all these G, such as this difference, this idea, and the index of the pair corresponding to the common projection for the last phase of this one, last phase of this one, is fixed. And that is a next concept. We have even symmetrical structures.
other Comments?
So of frames, but you mentioned balance equivalence.
Is that is that balance?
You mentioned balance equivalence of frames, and you mentioned also weak similarity. Weak similarity, and you put there localization. Is it is easy to explain me now what why you use localization and why you use weakly and why you use balance.
So the word localization comes from the fact that we are not considering as in the case of balance any invertible operation. We are not considering any possible invertible operation. We are just considering this restricted invertible operation.
Okay.
That would
Balance, which is balance doesn't require.
doesn't require that the invertible operator.
So there is no ideal.
But balance considers this notion for frames for the whole field.
Yes.
So when you have frames for half spaces, what would be balance notion equivalence becomes this weak. I mean that's not the point.
Okay, okay.
This is not mine. This is not ours.
So there is no ideal.
There is no localization.
Okay, and then weakly similar is balance.
Right.
Okay.
Any other question, comment? If not, we thank Pedro again.